Okay, lesson 44. You will notice it's kind of like what? 3 different topics here. The chain rule, which, yes, we've already done chain rule. This is just kind of a variation of a way to think about chain rule. Something I need to go over just so you're understanding the concepts here. We're also going to look at an alternate definition of derivative. So we already know a couple definitions of derivatives, but we're going to look at a couple others. An alternate definition of derivative and the symmetric definition of derivative. Okay? So, let's start with chain rule. Okay? The chain rule that I introduced back in whatever lesson that was. Also, if you recall, it came up on your AP classroom homework. Okay? But in order to take the derivative of a composite function, so a composite function being where there's a function within a function. Okay, so in order to take the derivative of f of g of x, this notation says you take the derivative of the outside, keep the inside, and then times the derivative of the inside. Sound a little familiar there? Derivative of the outside, or derivative of something, keeping something, and then times derivative of something is what I usually tend to say. Now, I'm going to do a different variation here that we're going to look at. And so again, dy dx. But what we're going to do is we're going to throw a u value in there. And so we're going to think of this as the derivative of y with respect to u times the derivative of u with respect to x. And again, this is going to work more based on how these problems are written today. It's technically the same chain rule, but we're going to work with a different method because of how the problems are set up. And I'll talk about both options, okay? So, now if you look here, it's saying that dy dx, dy du times du dx. That's equal because technically the du's can cancel, right? And so that's how the fact that it's equal. So let's look at example 1. Notice we're given 2 equations. Y equals u squared plus 4u, and u equals 5x cubed. They want us to find dy dx. So what I'm going to have you do is find the derivative of each of those individual equations before we set up what I just listed above of the dy du times du dx. Okay, so let's start with this one. It's y equal something in terms of u. So that means when I take the derivative of this, we're doing the derivative of y with respect to u, because there's u's in the equation. So derivative of y is just 1, right? We're going to say dy du. Derivative of u squared? Well, it would be 2u du if I had not already put the du over here. But since I put the du over here, we don't have to worry about that. Okay? Plus derivative of 4u. 4. Okay? This other equation is u equals something in terms of x. Means when I take the derivative of it, I'm doing du dx. Because it's the derivative of the u term with respect to the x's. So derivative of u, of course, is just 1 du dx. What's the derivative of that x term? What's the derivative of 5x cubed? 15x squared. Okay. So let's look at the rule I put up above. In that, dy dx is also equivalent to saying what? Dy du times du dx. Did we find dy du? Dy du is actually what? 2u plus 4. Times du dx. What's du dx? 15x squared. Okay? We can multiply those out, yes. However, when you multiply those out, what do you notice? We're going to have x's and u's in our problem. But we're supposed to be finding dy dx. So that's supposed to be the derivative of y with respect to x. Should I really have a u in my problem? Or my answer, I should say. Not really. Yep, you got it. What were we told about u? U is 5x cubed. So right there, take that 5x cubed value and plug it into u. So instead of saying 2u plus 4, what's that 2u become? Yeah, 10x to the third plus 4 and times 15x squared. Multiply it out, and you've got it. dy dx is equal to 150x to the fifth plus 60x squared. I agree. Now, I show that to you because I want you to, work to understand what's happening with the different derivatives, okay, and how they all come together. Curiosity, though. Just going to want to show you the equivalence. Is there a different way we could have done this problem from the beginning, if I didn't force you to go the way we just went? Plug you in from the beginning. Would that have worked? It would have. Let me show that as a side note. Again, I'm just trying to connect the dots here for you, so to speak. So if we would have taken this from the beginning, it's y equals u squared plus 4u. Y equals, well, u was what? 5x to the third, and then that's quantity squared. And it says plus 4u, so that's plus 4 times 5x cubed. Clean that up a little bit. 5x cubed, quantity squared would become 25x to the what? Not fifth, sixth, because it's power raised to a power, so you multiply. So 25x to the fifth, x to the sixth. I corrected you and then made my own mistake. And then 4 times 5x cubed would be 20x cubed. Now we have a y equation in terms of x. Could you take the derivative here? And you could. dy dx, so derivative of y with respect to all those x's, derivative of 25x to the sixth, 150x to the fifth, plus derivative of 20x cubed, 60x squared. And it does actually work out there. It does, we're not just randomly putting it down like, we got to match it. Okay? Both are good. I'm not complaining, in all honesty, we might like that a little bit better. However, I need to show this, introduce this, just so you see the connections, so you see how it all works together. So if you were to see something like this on the AP, you have various options depending on what they want. Okay? So that's why I'm not letting you just go for the sub it in from the beginning. Sorry. Okay. Let's try example 2. I'll be honest. We're going to use the du option here. We're not going to plug it in from the beginning. So we have a y in terms of v equation, a v in terms of u equation, and we're being asked to find dy du. So the y in terms of v equation, when we take the derivative of that, what is it that we're finding? dy dv, right? Because it's y equals, so derivative of y on top with respect to, this is in terms of v. What is the derivative of 2 natural log of v? Yeah, it's the 2, and the natural log of v is 1 over v. So 2 times 1 over v is 2 over v. Okay? V equals u squared. When I take the derivative there, it's the derivative of v with respect to u. What's the derivative of u squared? 2u. Now, will this work? We need to find what? dy du. Will that work when I multiply the pieces we just found? We just found dy dv and dv du. Will that give me dy du? Yeah, because my dv's will cancel, yes? Okay, so multiply the pieces. dy dv is 2 over v. dv du is 2u. But I don't want an answer in terms of v and u. What do I want an answer in terms of? I want everything to be used because u is the denominator. So what do we know about v? V is u squared. So it becomes 2 over u squared times 2u. What are you thinking? 4 over u? I agree. Because right now, if you multiply it as is, it's 4u over u squared. But you can reduce a u, and so that is 4 over u. Okay. And I'm not going to work out the other method for this one. That's the method that you're already more familiar with. So, example 3. Y equals sine of t. T equals 1 over square root of x. What is dy dx? So, y equals sine t. What do you need to find? dy dt. And what is the derivative of sine t? Cost.
Negative.
Cosine t.
I know you were waiting, so I was going to say it was negative.
Oh, you were just going to change it because you just thought I paused too long, huh? Nope. Okay. T equals 1 over square root of x. What is it we're finding? dt dx. What's my thought process here?
X to the negative 1/2.
Yeah. This right here to get us going is x to the negative 1/2, yes? So when we take the derivative of that, it is
Negative 1/2 x to the negative 3/2.
okay, yep, negative 1/2 x to the negative 3/2.
3/2.
I knew what you meant. On AP, you just have to be able to write it correctly. There's no voice test, so. Okay. So do we have the pieces we need? We're trying to find dy dx. What are the pieces I have? dy dt and dt dx. Will that work when I get done? dt's will cancel. So let's see, what's dy dt? Cosine t times dt dx negative 1/2 x to the negative 3/2. Okay, I've got a t and x. What do I want to be in terms of? Yeah, we want all x's because that's my denominator of dy dx. So what do we know about t? Yeah, 1 over the square root of x. So cosine of t is cosine, I wrote it as 1 over square root of x. You could also write that as x to the negative 1/2, it'd be equivalent. Still times negative 1/2 x to the negative 3/2, which, interesting enough, I just left that negative. Okay. You could leave it like that, or the one thing I would say, usually they tend to put any other type of other terms in front of the cosine term, just so it doesn't get mixed in with, is it a part of the insides of the cosine? So what you would more than likely see written is the negative 1/2 x to the negative 3/2 out front, and then the cosine of 1 over square root of x. Okay, so our chain rule using our differentials there. Okay. On the back side, we're talking about other forms of the derivative. We already know the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x, and the limit as h approaches 0 of f of x plus h minus f of x all over h. Those are essentially the same, except one uses delta x, one uses h, right? The h one's easier to write because it's easier to write h than a delta x. But other than that, they're the same. So now we have another form of the derivative. This talks about third form of the derivative. When given a value, x equals a, the limit as x approaches a of f of x minus f of a over x minus a. Okay, and this is just, it's usually defined as the alternate definition of derivative. It is a definition of derivative though. So noticing it's f of x minus f of a over x minus a. And it's the limit as x approaches that a. So not 0 this time, but x approaches that a. I kind of look at it as a way almost like a slope. So, okay, you ready to look at example 4? First thing I'm going to do, zoom out so you guys can see the whole problem, but I'm going to write down my definition from the front side. And it's the idea that f prime of a, so a derivative at value a, is the limit as x approaches a of f of x minus f of a over x minus a. And I'm just doing that because it's on the front side of the paper, and we're on the back side of the paper now, of course. Okay, so this problem says use alternate definition of the derivative to find f prime of a, where f of x equals x squared plus 1, and a is some constant. So we don't have an a value other than just a. Okay, you ready to try it? As ready as it gets, right? I shouldn't give the choice. Let's go. First of all, it's a limit, yes? So what should you be writing out front? Limit. The limit, in this case, they put in a, so it's the limit as x approaches a. Of f of x. What is f of x? X squared plus 1. Minus. What is f of a? But what is f of a? Huh? If f of x is x squared plus 1, f of a is a squared plus 1. I agree, it's a constant because a is some constant, but does that make sense there? That you're plugging a into the equation. So I'm going to be subtracting the quantity, a squared plus 1, all over x minus a. That's your initial setup. We've got to do some cleaning. The limit as x approaches a. What about that numerator? What does it clean up to be? X squared minus a squared. Because when I distribute that minus, it becomes minus a squared and minus 1. So 1 minus 1 will cancel. And I have x squared minus a squared over x minus a. Okay?
We can factor to cancel off the denominator.
Nice. Because right now, if I go plug that a into that limit, I'm going to have 0 over 0, which is not okay. X squared minus a squared. That is the difference of squares. So for instance, if this was x squared minus 25, can you factor x squared minus 25? That factors into x plus 5, x minus 5, right? So this is the same idea. It's just in terms of a's. So x plus a and x minus a. All over x minus a. And the whole point of that is x minus a's cancel. So I now have the limit as x approaches a of what? X plus a. What do you do to finish a limit off? Plug in the value, the approaching value. Okay. So instead of x plus a, I'm going to say a plus a, which is 2a. Okay. Does that make sense? Did you check yourself? F of x was x squared plus 1. What's the derivative of x squared plus 1? 2x. And then when you plug a in, it would be 2a. Yes, we took the long route, didn't we? Again, the definition of derivative always does that to us. Okay, this is another one to be able to recognize. You know, like definition of derivative, being able to recognize, oh, it's in that form. You'll see this form as well. Okay, so let's try it with example 5. This time we're not being asked to find f prime of a, we're being asked to find f prime of 1. So our a value is 1. So we're still going to use, remember that definition from above, or from the front page? We're still going to use that definition. It's just instead of finding f prime of a, I'm finding f prime of 1. So, it's the limit as x approaches what? 1. Because basically what? Every place you see an A, you're replacing it with 1, right? If you need that visual. Okay. F of x. What is f of x? X squared. Minus, my definition says f of a. Okay, so it's f of 1, which to be official, I'm going to write 1 squared, which I get is minus 1. Because it's what is f of 1, so 1 squared. All over x minus a, which is going to be in our case, x minus 1. Okay, so what we just did is f of x minus f of 1 over x minus 1. Okay, what do you know? Yeah, that top is x squared minus 1 squared, which is x minus 1, and so it factors into x plus 1, x minus 1. My denominator is x minus 1, so my x minus 1s can cancel. I have the limit as x approaches 1 of x plus 1. Which means what? Plug in 1, and big math, 1 plus 1 is 2. Now, does that check? Huh? You thought it was 11. Sorry, Daryl. Hate to be the bearer of bad news there.
You're right.
Okay. You can check yourself. F of x is x squared, so f prime of x is 2x. Plug in the 1. 2 times 1 is 2. Okay. Good to know we know our basic math today. Okay. F of x is the cube root of x. Use the alternate form of the derivative to find f prime of negative 1. Okay. F prime of 1. The limit as x approaches, f prime of negative 1. Better? Let's do the problem we're supposed to do. The limit as x approaches what? Negative 1. F of x, which is cube root of x, minus f of a, the cube root of negative 1 is what I'm going to write it out as. I'll clean up in the next step. Over x minus a. So x minus negative 1. Yep. I'll clean up in the next step, but yep, I agree, x plus 1. Okay. The limit as x approaches negative 1. Cube root of x. What is that as a power? X to the 1/3. Preparing for something else, so if you would, let's go x to 1/3. Minus, what's the cube root of negative 1? Negative 1. So minus negative 1 is really plus 1. Over x minus negative 1, which is x plus 1. What happens if I plug in my negative 1 right now? You get 0 over 0. You know the bottom is a 0, which right there, you know there's a problem, possibly. But then the cube root of negative 1 is negative 1 plus 1, 0. Okay, so think about the other two have factored, yes? We're going to factor that top. No. We're going to factor the bottom. My apologies. It is fancy math. Okay. I mean, essentially what we need is we need something to cancel, right? Specifically, an x cubed plus 1 or an x plus 1. Okay, here's the link that I'm going to do. So let me rewrite. Limit as x equals negative 1. We're going to leave x to the 1/3 plus 1 on top. It's going to stay as is. X. I want to rewrite my x using a 1/3 in there. So I want to say that x is x to the 1/3 raised to what power? The third. I promise I have someplace I'm going here. By doing this, x to the third, or x to the 1/3 raised to the third plus 1. I have just created the sum of cubes. Because 1 is a cube root. 1 is any kind of root, right? So 1 is a cube root. And now x to the 1/3 raised to the third, I can take the cube root. You guys remember how to factor sum of cubes? This is one where it factors into a binomial times a trinomial. Where I think this book uses f cubed plus s cubed, if I recall.
I remember seeing that now. Oh no.
Factors into f plus s
Exactly.
and f squared minus fs plus s squared. Now, it's normally pretty doable. This time we're throwing in a fun fraction exponent, which makes it a little more tedious.
That's the part of lesson 2 we got today.
That's part of lesson 2?
Yeah, we didn't get the quadratic formula, but we got that.
Okay, there you go. See, I'm still back in lesson 2 today. Okay, so it's the limit as x approaches negative 1 still. It's still x to the 1/3 plus 1 in the numerator. My denominator is factoring into a binomial times a trinomial because it's two perfect cubes. Now, if it's f cubed plus s cubed, f plus s represents the cube roots. So what's the cube root here? If it's x to the 1/3 raised to the third, the cube root is the x to the 1/3. Plus, what's the cube root of 1? 1. First parenthesis. Okay, second parenthesis. F squared. So your cube root here, squared. So yes, x to the 1/3 squared becomes x to the 2/3 minus these two cube roots multiplied. So 1 times x to the 1/3 is just going to be x to the 1/3 plus f squared. So this cube root squared. 1 squared is 1. All of that fancy math and what did happen? X to the 1/3 plus 1 cancels. We better be able to cancel something. So, my current problem is x to the limit as x approaches negative 1. If everything cancels on top, that means we have a 1 over x to the 2/3 minus x to the 1/3 plus 1. Plug in your negative 1. I know I have 1 on top. X to the 2/3. That's the cube root of negative 1, which is -1, then squared, which makes it +1, minus x to the 1/3. The cube root of -1, -1. So really it's minus -1, and then it is +1. Which gives me
1/1. I thought you were serious for like half a second. I was like, Nathan, no.
I was like, I heard 1/, and I was like, that's not 3. Man, he's way off in his answer. Oh, wait, never mind. We're back to the joke of the day. Got it. Okay. I'm going to go with 1/3. Nathan can have his 1/111. Whatever you guys want to do there.
It is 1/3. It's just 3/7.
Or 1 over Roman numeral 3.
Yeah.
Okay.
We're smart.
Anyways,
Equivalent answers.
there goes any chance at a passing score.
Nathan does all of his math in Roman numerals. Would they still be able to count that right if you did all the math in Roman numerals and got the right answer?
I doubt it, because how can you tell it's Roman numerals as opposed to variables?
You'd write it
They're gonna
at the
see-
top. You'd be like, this is in
Yeah.
Roman numerals.
Don't plan on getting credit for that.
You put the lines over them so they're like connected.
Okay,
And then, IV, and then you put the lines on top of the parentheses.
one more derivative for the day. This is what is referred to as the symmetric derivative. Symmetric derivative, well, think about the word symmetric, and hopefully you see a symmetric quality here.
No, I see a plus and a minus, and it's symmetrical.
Anyways, the limit as h approaches 0 of f of x plus h minus f of x minus h all over 2h. It's a variation of our original definition of derivative,
Why are there so many types of derivatives?
because that's one of our big 3 topics in Calculus AB. Okay, use the symmetric derivative to find f prime of x, where f of x equals x squared plus 15. Here we go. F prime of x. The limit as h approaches 0. F of x plus h. How confident are we feeling with that?
X plus h squared plus 15.
Uh-huh. Here's my side note if you need a little help there. If f of x is x squared plus 15, every place you see an x, you're going to replace. So if I'm trying to find f of x plus h, every place I see x, I'm replacing with x plus h. So if it was x squared, I'm now going to say x plus h squared plus 15. I know, some years my classes really struggle with that, some years not so much. Depends on the day.
If it's a Tuesday, I got it. Thursday, I don't know if I can do it.
Friday.
What about Friday? No chance?
It's a wild card day on Friday.
Okay. The limit as h approaches 0. So f of x plus h is going to be x plus h squared plus 15 minus f of x minus h, which means x minus h squared plus 15. And notice I have that whole parenthesis, that whole quantity in parentheses. All over 2h.
That's not symmetrical.
Okay, limit as h approaches 0. What do you think I have to do here?
Plug in 0 and say undefined.
Yes.
Nice try.
From their X's.
All right.
You plug in 0 right now, you're getting 0 over 0. That's a problem. Okay, so plan B.
You can cancel the 15s.
You can cancel the 15s. You're going to have to FOIL the other pieces out. Yep. So I'm going to go ahead and just FOIL it all out right now. And then the 15s will cancel, along with some of our foiling pieces will cancel. So x plus h quantity squared. What does that FOIL out to be? X squared plus not just xh, 2xh plus h squared. Plus the 15, which, as Sarah pointed out, yes, those are going to cancel. Now, notice it's minus this whole next quantity. How talented are you guys? Can we do this and change the signs at the same time? Okay, so when you FOIL x minus h squared, let's just talk about it. What is x minus h squared when you FOIL it?
X squared minus 2xh plus h squared.
Right. X squared minus 2xh plus h squared. Now, since I'm subtracting all that, as I write it down, I'm going to write those opposite signs. Are we okay? So I'm going to say minus x squared plus 2xh minus h squared. And then officially it's also minus 15 all over 2h. Okay. I was already informed 15s cancel. Got some other canceling magic for me? X squareds? H squareds? 2xh plus 2xh. 4xh over 2h. Got some more canceling magic for me? Okay. H cancels, and then you can leave the 4 and 2 if you want, or could you cancel a 2 if you caught it? And so you have the limit as h approaches 0 of 2x. Plug in 0 for h, except I have no h's left, so it's 2x. Does my answer check? Yeah, because our basic power rule tells us the derivative of x squared plus 15 is 2x. It's definitely a Friday.